Hello everyone, welcome to our discussion of section 10.7 where we will be talking about partial fractions decomposition. So what is this topic all about? Well, typically we always take the common denominator to combine two or more fractions, right? This is what you've been doing so far. In every class you've taken, including this one, whenever you had several fractions, we always asked you to simplify that, which meant as part of that, you had to combine or take the common denominator to combine those fractions. So let's do a couple of examples of that right now, just to remind ourselves what that procedure was about. So in this case, we have different denominators. We wanted to find the common denominator. In this case, it would be 12. So if the common denominator is 12, then each of these should match that. So to match 3 to 12, we would have to multiply the denominator by 4. But of course, we can't do this to the denominator and not do the same thing to the numerator. So we would also multiply the top by 4. The 4 should also match the common denominator. To do that, we'll have to multiply this by 3. And of course, we have to do the same thing to the numerator. We multiply it by 3. And the last fraction, this denominator has to match the common denominator. So we have to multiply it by 2. Of course, we have to do the same thing to the numerator. Then the denominators are all 12. Now the numerator here would be 8 plus 1 times 3 is 3, minus 1 times 2 is 2. Now we would say 8 plus 3, 11, minus 2, that's 9 over 12. And of course, we would even ask you, hey guys, don't leave it like that. Simplify this. So we know that 3 is 3 times 3, 9 is 3 times 3, 12 is 3 times 4. And so we would cancel these two, and we would end up with the final result of 3 over 4. Okay? This is what we typically did if we had three fractions like that. Now, if we had two rational functions, these are called rational functions because they're fractions with x in them, like that, we would do the same thing. So the common denominator in this case is this expression times that expression, right? So let's write that down. So we would say that the common denominator is that times 2x plus 1, right? So we do the same thing here. We'd have to match each of these denominators to the common denominator. So compare this common denominator with this. What's missing from it is 2x plus 1. So we would multiply the top by 2x plus 1. So this 1 times 2x plus 1 plus, then compare this common denominator with this one. What's missing from it is this x minus 1. So we would multiply the top or the numerator by what's missing from it, which is x minus 1. This is exactly the same procedure as that, but the difference here is that we have rational functions. They look a little bit different, right? Like that. The next step, of course, is distribute these, combine the like terms, and simplify the expression as much as we can. So let's do that. 1 times all of that, we get the same thing back, plus 1 times all of that, we get the same thing back, divided by the denominator in factored form. So keep the denominator in factored form as long as it's possible. Like that. And then, of course, let's combine the like terms. 2x plus 3 plus x is 3x. And then 1 minus 1 is 0. So we end up with 3x over x minus 1 times 2x plus 1. So this would be our final result. Okay? Beyond which we cannot simplify this any further. So remember, this is what we used to do so far. Now with partial fractions, and so I've written down this little excerpt to remind you in your notes that in some situations though, especially in calculus, we need to find the original individual fractions or rational functions. So we want to find these. So we are given this form in calculus, and we need to find these. You might ask, well, why is that? Why after learning to go from this to that, now we want to go backwards? Well, it just turns out that in calculus, starting in calculus 2 and higher, calculus 3, differential equations, and on, there are some techniques that you're going to learn in those classes such that it would be very, very difficult, if not impossible, to apply those techniques to this rational function. But it would be very easy to apply the same techniques to these two individual fractions. In those situations, we want to be able to go from here back to this form so that we can apply those techniques we learned in calculus and differential equations. That's why this is a very important technique beginning especially in calculus 2, calculus 3, and differential equations classes. Okay? So that is the reason we're learning about partial fractions. All right, so now, before we attempt to find partial fractions, so before we see how we can find partial fractions, we need to remember, very important, we need to remember the following skills and techniques we have learned in the past. So, in other words, partial fractions is a converging point for many different techniques you've learned so far in this class and maybe even before this. But we've learned about all these skills in this class. Factoring polynomial, you've seen this maybe even in college algebra, but for sure we've done this so far in this course. Long division, for sure we've done that. Solving systems of linear equations, we did this in college algebra, we're doing it in pre-calculus 1 here, and so we need to know how to do that. Completing the square in a quadratic equation, so that we've done this a couple of times, especially when we were finding the standard equation of a circle. Do you remember that? When we did that, especially we needed to do that. And sometimes, just for fun, we applied this to quadratic equations that we had. We just used this to put them in standard form so that we can immediately look at them and say, oh, the coordinates of the vertex of the quadratic equation are as follows. And we used this technique to accomplish that. 5, multiplying both sides of an equation by the least common denominator in order to clear all rational functions on both sides. So we have a technique, we did this when we solved rational functions previously in this course. We used the technique to clear all fractions on both sides to solve for x. Remember that? So we're going to need to remember that here. And number 6, recall that in a quadratic equation, which has this form, when the discriminant this is what we call the discriminant, is less than 0. So when the discriminant is negative or less than 0, then the quadratic equation cannot be factored. That's how we can predict whether we have a factorization of the quadratic function or not. If the discriminant is negative or less than 0, then the quadratic equation cannot be factored. And when this happens in the denominator of a fraction, we do not need to use partial fractions. I could also say when this happens in the denominator of a rational function rather than fraction, it would be better if I said rational function. We do not need to use partial fractions. So this is a test. If you have a quadratic function, quickly do this test. If it's negative, if the discriminant is negative, then you don't have to use the partial fraction. There are other techniques we should use. With the above techniques and knowledge in mind, there are 4 cases for investigating or finding partial fractions. Very important. And we're going to look at all 4 cases in this section. Okay? So case 1, which is this, would be given a rational function like this, p of x over q of x, such that the degree of the numerator, so we call the numerator some polynomial p of x, is less than the degree of the denominator q of x, and such that the denominator q of x is a product of distinct linear factors, none of which are repeated. If we have this kind of a rational function in this form, then that's considered case 1. So you might say, well, that's not good enough because I need to see an example. And that, I agree with you, and that's exactly what I have in mind next. So the example we're going to look at is this one. So this would be obtain the partial fractions for this rational functions. You see that? Well, this is what we mean, if I bring the previous slide back, this is what we mean by when the q of x such that the denominator here is a product of distinct linear factors, none of which is repeated. So look at the denominators. You have linear factors, right? X minus 3, x minus 2, and neither one of which is repeated. So you might be wondering, well, what does it mean if they were repeated? How would we notice that? Well, if any of these factors, if any of these denominators were repeated, you would have a power higher than 1. So you would have x minus 3 squared, or x minus 3 cubed, or x minus 2 squared, or cubed, or to some other power than positive 1. That would indicate that this would be what is a repeated linear factor. But in this case, we have distinct linear factors, none of which is repeated. Okay, so that is case 1. And if you have any questions about this, please drop by my office hours after watching this video lesson. But let's go through this example to see how partial fractions work. So the first thing we do is we break this apart into 2 fractions as follows. So we have x minus 4 divided by x minus 3 times x minus 2 equals a divided by this denominator, x minus 3, plus b divided by this other linear factor, x minus 2. Okay? So our task here is to find a and b, because once we find those, we found the partial fractions. Okay? So the first thing we want to do is we want to remove all these expressions on both sides from fraction form. That was one of the skills we needed to know before we find partial fractions. Remember, that was on the list. So let me write that here. So to remove fractions on both sides, we want to, you've done this before previously, but we're going to have to do it here for a different reason, right? We're finding the partial fractions, multiply both sides by this denominator, right? Because we know that if you multiply both sides by this, it will clear this fraction, this one, as well as that one. So multiply both sides by x minus 3 times x minus 2. Let's do that. So I'm going to do this step by step, so you guys can follow this, but if you can do it faster, then do it faster. But I want to make sure that everybody's following this procedure, so I'm going step by step. By the way, after this first example, the next examples, pause the video as soon as I write down the example solve it on your own, then come back to the video to see how I solve the example, okay? But this is the first example, so it's okay if you want to watch the whole thing and as I move forward. So I'm going to multiply the left side by this, because I know that will clear this fraction, right? Times x minus 4 divided by x minus 3 times x minus 2 equals, we can't, with equations, we can't do one thing to one side and not do it to the other side, right? We've discussed this before, guys, so I expect you to remember that. So let us multiply the same thing on the right side. So multiply that by a over x minus 3 plus b over x minus 2. Now we've multiplied both sides by the same thing. Okay, now I'm going to, on the left side, things are really, really easy, right? Because this x minus 2 and this x minus 2 cancel each other out, and this x minus 3 and this x minus 3 cancel each other out. We end up with x minus 4, right? But on the right side, things are a little more interesting. So I'm going to distribute this whole thing into this first fraction and then simplify. This is what I was saying. If you're comfortable to simplify at this point, do it. But I'm going to do it step by step. So x minus 3 times x minus 2 times this fraction, a over x minus 3, plus, because we're distributing these two factors into this bracket, right? So again, x minus 3 times x minus 2 times b divided by x minus 2. So do you see what I did? I just distributed this into each fraction. Now, let's start simplifying the right-hand side, because the left-hand side is happy the way it is, right? That we don't want this to be more simplified than that. So we have x minus 4 equals, we have this x minus 3 and this x minus 3 canceling each other out. We end up with x minus 2 multiplied by this a, right? And then plus, in the next term here, x minus 2 and x minus 2 cancel each other out. We end up with x minus 3 times b, right? This times that. Look at that. We've gotten rid of all fractions, didn't we? So that's what we intended to do. So now, on the right side, of course, we need to distribute these, right? Because look, we have x terms and we have constants. We need to separate these. So we need to distribute a into this and b into this. Let's do that. A times x is ax. A times minus 2 minus 2a. And then plus b times x is bx. B times minus 3 is minus 3b, right? Now, just like before, you've done this 100 times. You've combined the x terms. So let's do that. So we have x minus 4 equals, I'm going to put them in parentheses just to group them for now. So we have ax plus bx. I'm doing this because both of these terms have x in them. And then plus, let's group the constant terms, right? The terms that have no x in them. So minus 2a minus 3b, right? Oops, sorry, I was off the screen. My apologies. Let me move this up. So after I distributed, what I was saying is that after I distributed this on the right side, now I'm grouping the terms that have x in them plus the terms that have no x in them, right? I just put parentheses just to show that I'm grouping them. That's all. Now, let's factor out the x from this group. So we have x minus 4. We have x minus 4 equals a plus b times x, right? I just factored out x from this group, plus the same group, let's write it down. Minus 2a minus 3b, right? Now, everything we've done so far, notice how detailed. We were down in the details, right? Whatever we did. Now, zoom out. Now, I want you to zoom out, right? Let's step away from this detail work. Let's zoom out and look at the whole big picture here. Now, if the left side is to be equal to the right side, what should a plus b be? Because we have x, but the coefficient of the x on the left side is positive 1, right? So if the left side is to be equal to the right side, a plus b cannot be different than positive 1. So let's create a system based on that. So we say that I'm going to write a system. In the items that I listed, that the list of skills and techniques we needed to recall to understand partial fractions, one of them was solving systems, right? Now you see why I listed that. So a plus b must be equal to 1. I hope you see why I'm saying this. Otherwise, if a plus b is not equal to 1, which is the coefficient on the left side, then the left and the right cannot be equal. But we're saying that the two sides should be equal. So the coefficient of x on this side should be equal to positive 1. We know what the coefficient of the x is on the left side, but we don't know what it is on the right side. But we do know whatever a and b, they should add up to 1. Otherwise, we can't have this equation. So a plus b must be equal to 1. Now, what about this constant? Now, this group must be equal to negative 4. Do you see that? Do you see why? So if this is different than negative 4, then the left and the right cannot be equal. So for this side to be equal to that side, all of this, minus 2a minus 3b, should add up to minus 4. So let's write that down as well. Minus 2a minus 3b must be equal to minus 4. Okay, so this is like any system you've solved before. All we have to do is solve for a and b, and we know how to do that, right? So I'm just going to, either a and b are easily solved for. I'm just going to multiply the top row by 2. You can use any method that you prefer, just to get rid of the a terms. You can get rid of the b terms and end up with the same answer. So it doesn't make any difference. So multiply the top row by 2, we get 2a plus 2b equals 2. And the bottom stays the same for now, right? Minus 2a minus 3b equals minus 4. And we add these two equations and we get, so these 2a plus minus 2a, they add up to 0. 2b plus minus 3b is minus b on the left equals 2 plus minus 4, that's minus 2, right? So we have, at this point, we have b equals 2, right? So now we can plug this b into any of these equations and solve for a. The first equation is pretty simple, so we can say using a plus b equals 1, which is that one, then we have a plus 2 equals 1, therefore a is equal to minus 1, right? So we figured out b, we figured out a. Now we can plug back into our partial fraction decomposition. We know a, we know b, we are able to find the partial fraction decomposition of this rational function into that. So let's do that. Let me do that maybe here. So I will do that here. And so we started with this fraction. I will rewrite it so it's on the screen. So we said x minus 4 over x minus 3 times x minus 2, right? Which was equal to a over x minus 3 plus b over x minus 2, right? This is what we started with, which we cleared fractions, and then we wrote the systems and such. So let's plug in for a with -1 and b with 2. So we have the final result is it will be x minus 4 divided by x minus 3 times x minus 2 equals -1 divided by x minus 3 plus 2 over x minus 2. Okay? You can, so this would be good enough. You can, if you want to, switch things around so this minus is in the middle. You can do that too. So you can say this is my final answer, or you can continue and say x minus 4 over x minus 3 times x minus 2 is equal to 2 over x minus 2 minus 1 over x minus 3. That way this minus is in the middle. So this would be our final partial fraction decomposition of this expression, which is what we started with, right? Like that. So now, earlier I said we do this because starting in calculus 2, we have techniques that can easily apply to this partial fractions, but it will be very difficult or impossible to apply to this side. So this, in calculus 2, you'll really appreciate why we do this partial, why we learn about partial fractions. Okay? All right, so that was case 1. Now case 2 will be of this kind, like that. So it says, given a rational function like that, with polynomial on top, polynomial in the denominator, such that where q of x, which is the denominator, is the product of linear factors, some of which are repeated factors, then we must do this. Before this, let me show you what I mean by repeated factors. So this is the example we're going to do for this case 2. Notice that we have a linear factor here and a linear factor here, x minus 2, 2x plus 1. But this one is repeated, right? Because you have x minus 2 squared. So what does that mean? That means x minus 2 times x minus 2, right? If you expand x minus 2 squared, it's x minus 2 times x minus 2. So it's repeated factor, that one. So that's case 2. So the denominator is the product of linear factors, some of which are repeated factors. Then we must do this. Factor q of x, if it's in case qx is not already factored, right? In the example I showed you, it's already factored. But if it's not factored, we have to factor it to the extent possible. Then only if the degree of the numerator is larger than the degree of the denominator, use the long division to obtain this, to convert what we have to sx plus rx over qx. Sometimes you encounter this. Not often, but it's there, especially when you get to calculus 2. Now and then you get rational functions such that the degree of the numerator is larger than the degree of the denominator. So you have to use long division in such cases. So note that once we apply the long division, then in this rational function, so if you have to use long division, you go from here to this, right? This would be your remainder. So in this case, the degree of r of x is now lower than the degree of q of x. It has to be. After the long division, the degree of r of x will be lower than q of x, which is what you want before you find the partial fractions for this piece. Because you don't need to find the partial fractions for this piece, you would need to find the partial fractions for this one, because it's a ratio, it's a rational function that we have. Okay, so then after that, if we didn't have to use long division, that means we're using the original rational function with the degree of p of x smaller than the degree of q of x. We need to break this up, just like what we did in case 1. Or if we had to use the long division to make the degree of this polynomial lower than this, so we have Rx in this case, right? We're going to have to deal with this one. We either have to break up this one or this one as a sum of partial fractions of the form a over x plus b. Okay, so this is just this page 5, is just describing what case 2 is doing. So if you ever forget how this is done, you can come back to this sheet of paper and remind yourself how this is done. This is a description of what we will be doing. But nothing is better than just going through an example, right? Practically seeing how this works. And we're going to do that. So we have, it says obtain the partial fractions for this expression. You can see there is a quadratic equation in the numerator, and we have two factors, linear factors in the denominator, one of which is repeated, right? So let's see how case 2 works, how we should split or break apart this one. By the way, here, as you can see, the degree of the numerator is lower than the degree of the denominator, right? Because this x squared times this x will give us x cubed. So x squared is lower than x cubed. So we do not have to use long division in this case. If we had x to the 4th power here, then yes, we'd have to divide this by the whole denominator using long division. So let us write the first, let us break this apart for the way we should for case 2. If you want, you can pause the video at this time and just so that you can write the next step for a few seconds and then come back to the video and see how I did it. You can do that if you want to do. That's a good idea. So for this linear factor, I'm assuming you've done that and now you're back. So a over this linear factor 2x plus 1 plus b over this factor to the lowest power, 1, x minus 2, because it's repeated, right? Then plus c over x minus 2 squared. You see that? Whenever you have linear factors that are repeated, this is what you'll have to do. Suppose if we had x minus 2 cubed, then what? Then I would have to say plus d divided by x minus 2 cubed. So we'd have to start from the lowest power, 1, 2, and then 3. What if I had x minus 2 to 4th power? I would have to have e. After d, I would have to have e over x minus 2 to 4th power. You see what I'm saying? So if you have any questions about that, please come to my office hours. So now the task is, once we break this up into the preliminary partial fractions, now our task is to clear all these fractions. So multiply both sides by this whole denominator, right? By 2x plus 1 times x minus 2 squared. Now I'm going to do the same thing as I did before. I'm going to do this step by step so everybody can see how this works. I highly recommend and encourage you to pause the video at this point. Don't look at the rest of the solution. Do this and continue on your own until the finish. Then come back to the video and see how I did it. Okay? So I'm assuming you've done that, and now you have your own solution in front of you. So I'm multiplying the left side by that whole thing, because I know that will clear that fraction, right? Because that's the same thing as that. So x squared minus 5x plus 16 divided by 2x plus 1 times x minus 2 squared, close bracket, equals, now I'm going to multiply the right side, all of the right side, by this. So we have 2x plus 1 times x minus 2 squared times a over 2x plus 1 plus b divided by x minus 2 plus c over x minus 2 squared, like that. All right? Now, on the left side, things are wonderful, right? Because this will cancel out with this. This whole thing cancels out with this thing. So we end up with this expression. We end up with, let me move this up a little bit. We will end up with just that, the numerator. So which is x squared minus 5x plus 16. On the right side, I'm going to distribute this to each fraction. This one, then this one, then this one. Okay? So we have 2x plus 1 times x minus 2 squared times a over 2x plus 1 plus all of that, 2x plus 1 times x minus 2 squared times b divided by x minus 2 plus, right? I'm going through and distributing this to each fraction. Again, that whole those two factors, 2x plus 1 times x minus 2 squared times c divided by x minus 2 squared, close bracket. Okay, so now let's go through and simplify the things we can. So on the left side, things are good. So we just write x squared minus 5x plus 16. Now look what happens here. This 2x plus 1 and this 2x plus 1 cancel each other out. We end up with x, this factor, x minus 2 squared times a, don't we? That's what we get. Look how nicely the fraction is gone. Now we do the same thing here. Notice that x minus 2 has power 2. So this x minus 2 goes away or cancels out with one of this, but we have one, because this has squared power, so we still have an x minus 2 coming from this factor, right? We have one factor x minus 2 coming from this. We couldn't, because this one wasn't squared, so we couldn't get rid of both of them. But it's nice, we still got rid of the fraction this way, right? So we have plus 2x plus 1, which is this factor, times the remaining factor of x minus 2 squared, the remaining one is this, to power 1, times, of course, b, like that. And finally, we have x minus 2 squared and x minus 2 squared, so we're left with 2x plus 1 times c. Okay? All right, so what do we do now? Well, there's plenty for us to do yet, right? For example, we need to expand this, then distribute a to it. We also need to distribute b. We need to FOIL these two and then distribute b into it. So there's a lot for us to do, so let's do that. So I'm going to start from the left side again. We have x squared minus 5x plus 16. Let me expand this. If we expand this, what do we get? We get x squared minus 4x plus 4 times a, right? Plus, let's FOIL these two. What are we going to get? We're going 2x times x, 2x squared. 2x times minus 2, minus 4x. 1 times x, just positive x. 1 times negative 2, minus 2. All of that times b. And here, we can distribute the c into this, right? So let's do that. So we have 2cx plus c. All right. So before we do the next step, notice that we can combine these two, right? Minus 4x plus x gives us negative 3x. Good. So we combine those. Now let's go through and start simplifying the right side a little more. On the left, things are good, right? We don't have to do anything on that side. Minus x squared minus 5x plus 16 equals, now I'm going to distribute a into everything that you see here. So a times x squared, we get ax squared. A times minus 4x, we get minus 4ax. A times 4, we get plus 4a, right? So now let's distribute b into everything here. I'll move this up a little bit. So b times 2x squared, we get plus 2bx squared. B times minus 3x, because these two combine into this. So b times minus 3x is minus 3bx, right? B times minus 2, minus 2b, right? And then, of course, the last two terms, which we can just write them down as they are, like that. All right. So what do we do now? Do you remember what we did for case 1 at this point? Well, we have to look at what are the like terms. We have to group them. So anything that has x squared attached to it, I'm going to group them. Anything that has x in it, this one, and that one, I'm going to group those. And anything that is a constant without any x in it, like that one, and that one, and that one, I'm going to group all of those. So let's do that. So x squared minus 5x plus 16 equals, on the right side, we have two terms that have x squared in them, right? So let's group them in a parenthesis. So ax squared plus 2bx squared plus, now we're going to group anything that has x in it. This one, and that one. Three terms have x in them, right? Minus 4ax, that one. Minus 3bx. Then plus 2cx, right? Plus 2cx. And then plus anything that is a constant. So constants are this one, right? There's no x with it, so that's a constant. So we have 4a. And then what else? We have minus 2b. And then, of course, we have plus c, right? So plus c, and we have a group there. After we form the groups, now let's factor out x squared from this group, x from this group, right? So we're going to have x squared minus 5x plus 16. Left side is all good, right? We don't have to do anything on that side. All we did was clear the fraction. So let's factor out the x squared. What are we left with? A plus 2b times x squared plus all of this factored out. So minus 4a minus 3b plus 2c with x factored out here, right? We're pulling out the x from this group. We pulled out x squared from that group. The last group doesn't need any factorization. It's just a bunch of constants. So let's write them down as they are, like this. Okay? So far, so good. Does this make sense? If it doesn't, you should come to my office hours, please. Now, like before, we have done a lot of detailed work. Look at that. It's all very detailed, right? Now it's time for you to zoom out. Zoom out. Go and look at the big picture here. What's the big picture? The big picture is that in order for this side of the equation, I wish I had my highlighter, but let me use my red ink here. We're saying that in the big picture, the left side is equal to the right side, right? If that's true, then the coefficient of the x squared on this side should be equal to the coefficient of the x squared on that side. The coefficient of the x on this side should be equal to the coefficient of the x on that side. And the constant on this side should be equal to the constant on this side. So this is now how we set up where we need to set up the system. So we say, based on that discussion, a plus 2b must be equal to positive 1. Then all of this, minus 4a minus 3b plus 2c, must be equal to minus 5, right? Because these are the coefficient of x. They should all add up to minus 5. Otherwise, the left and the right will not be equal. So minus 4a minus 3b plus 2c must be equal to minus 5. And all of that, all 4a minus 2b plus c must be equal to 16. So let's write that down. 4a minus 2b plus c must be equal to 16. Okay? This transition from detailed work to big picture is very important. This is critical. If you don't follow from here to here, you must ask questions, either in class or during my office hours, please. All right. So then we continue. And let me go to the next page here. I'll keep this on the screen like that. Right? So now, notice that we have three equations, three unknowns. Typically, we would go through checking to see which variable is easier to eliminate. But in this case, look at the first equation. It's already missing variable c. So let's get rid of the variable c in these two equations. That's because the first equation is kind of hinting us to do that. So let's get rid of the c. So I'll write this down. Let us eliminate c in the last two equations there. In the last two equations. Okay. So let me write them down here. So we have minus 4a minus 3b plus 2c equals negative 5. 4a minus 2b plus c equals 16. So you can do whatever you prefer, but I'm just going to do elimination method. You can do substitution if you want. I'm going to use elimination, multiplied, and I'm going to multiply the bottom row with this. We don't need the previous slide anymore, so I'll take it away. And so we'll deal with just this page. And so here we have the top equation stays the same. Now we distribute this to the whole equation. So minus 8a plus 4b minus 2c equals minus 32. So let's add these two equations. Now we meant to eliminate c, right? So that we can certainly do. 2c plus minus 2c add up to 0. Minus 4a plus minus 8a gives us minus 12a, right? Then minus 3b plus 4b gives us positive b equals minus 5 plus minus 32 gives us minus 37. So this equation is the reduced equation in variables a and b. So reduced equation with variables a and b. A and b. Okay? So now, remember that we had that, I should bring back that previous slide. We had that equation, a plus 2b equals 1, right? And we reduced these two to a smaller equation of a and b. So let's make another system of these two reduced equations. So let me write it here. So we have a plus 2b from the previous slide equals 1. We have this one. Let's combine them. Minus 12a plus b equals minus 37. So now it looks like that the b variable is easier to eliminate, right? So I'm going to multiply the bottom equation with minus 2. And then we have, so we have a plus 2b equals 1. And then we have minus 2 times minus 12. That's 24a. Minus 2 times b minus 2b equals minus 2 times minus 37. That'll give us positive 74, right? Positive 74. Okay, let's add these two equations. What do we get? We get the 2b plus minus 2b, they add up to 0. We end up with a plus 24a. We end up with 25a, right, equals 1 plus 74, we get 75. And then we're solving for a, which means we need to isolate a. Is a isolated right now? No, it's got a 25 next to it, so we need to get rid of this 25 to isolate a. So how do we do that? We divide both sides by 25. Of course, these cancel out on that side. We end up with a equals 3, right? 75 divided by 25, 3. So we found a. Now, using any of these two equations, we can solve for b. So using, let me write that down. So using a plus 2b equals 1, and the fact that we figured out what a is, and a equals 3, we have, let's plug in and solve. We have 3 for a, plus 2b equals 1. That means that 2b is going to be equal to 1 minus 3, and 2b equals minus 2. And now, again, we're solving for the variable b. That means we need to isolate b. Is b isolated right now? No, it's got a 2 next to it, so let's get rid of it. How do we do that? We divide by 2 because it was being multiplied by b. So we get rid of it by dividing both sides by 2. So we get b equals negative 1 on that side, right? So we solved for a. We now solve for b. And then, so now we have to solve for c, right? So for that, we can use any of these equations. Let's use that one. Let's use that one, right? So using, I'll just write it here, using this equation for a minus 2b plus c equals 16, And let me move this down. So you have a and b shown here. Let's plug in. 4 times 3 minus 2 times b, which is negative 1, plus c must be equal to 16. So we have 12 plus 2 plus c equals 16. We have c, 12 and 2, 14. Move it to the other side. We get c equals 16 minus 14. Therefore, c equals positive 2. Here's c. So we have a, we have b, we have c. So now we can go back to the partial fraction that we set up at the beginning and plug in. So let's do that on the next page. So thus, we have figured out, we have these a equals 3, b was equal to minus 1, and c was equal to 2, right? I'm just double checking, correct. And recall that we started with this, right? Recall that we started with this expression, x squared minus 5x plus 16 divided by 2x plus 1 times x minus 2 squared equals a divided by 2x plus 1 plus b divided by x minus 2 plus c divided by x minus 2 squared. Remember that? We set out to figure out a, b, c. We did that. Now we're going to plug in. So we end up with, I'm just going to plug those in. So x squared on the left, we have x squared minus 5x plus 16 divided by 2x plus 1 times x minus 2 squared equals, a is 3. All right, let me switch colors here. 3 over 2x plus 1 plus b is minus 1, minus 1 divided by x minus 2 plus c is equal to 2, so 2 over x minus 2 squared. Now this minus is going to multiply itself by this plus and change it to negative, right? So let's change it anyway. So let's change it. So we have x squared minus 5x plus 16 divided by 2x plus 1 times x minus 2 squared equals 3 over 2x plus 1 minus 1 over x minus 2 plus 2 divided by x minus 2 squared. So there we go. We have achieved what we set out to do. So I want to remind you, in Calculus 2 and beyond, we have methods that would be impossible or extremely difficult to apply to this fraction, rational function, but they would be extremely easy or very easy to apply to these. That's why we're doing this. We're preparing you for using those techniques. Okay? Very, very important topic in calculus and higher. So this was case 2. Case 3 is as follows. So we have a rational function, f of x equals p of x over q of x, such that q of x, or the denominator, contains irreducible i.e. non-factorable quadratic factors. Irreducible, that's a term your book uses, and I'm using it, but I'm defining it here. Irreducible means non-factorable quadratic factors in the denominator. Read this carefully. Given this rational function, q of x, the denominator, if that contains irreducible or non-factorable quadratic factors, this occurs when the discriminant is negative. When b squared minus 4ac is less than 0, that's when we cannot factor the quadratic equation, none of which is repeated. So they cannot be repeated, of course, if the degree of the numerator p of x is larger than the degree of q of x, we must use long division as well. So the purpose of this piece from here to here is just to remind you to check with the degree of the polynomial in the numerator and the degree of the polynomial in the denominator. If the numerator degree is higher, you have to use long division before you can apply partial fractions. It's just reminding you of that here. Okay? Before you use partial fractions, you have to use long division if degree of p of x is larger than the degree of q of x. Okay? So let's see an example of this kind, in case 3. So here we have an example of this kind. Let me write this here, and you'll see how we obtain the partial fractions for this case, case 3. So x cubed minus 2x squared plus x plus 1 divided by x to the 4th plus 5x squared plus 4 equals, so before we do the format, we need to factor this out, right? We need to factor that out. So if you do that, it would be a good exercise if you pause the video at this stage. Don't look at how I factor this denominator. Pause the video, do it, and then obtain your factors and come back. It shouldn't take you more than a minute or less, or a couple of minutes. Just think about it. I want you to think about it before you see my factorization. Please pause the video and do it. So I'm assuming you've done that, and now you're back. So hopefully our factorization agree together. So we want to factor this. So the factors are x squared plus 1 times x squared plus 4. So notice in that description, we said that case 3 is when q of x, or the denominator, contains irreducible or non-factorable quadratic factors. Right? What do you see now? These two factors, they're both quadratic and they're both irreducible. Right? Because can you factor this one any more than this? No. Can you factor this one? No. And none of them are repeated, right? In other words, you don't have a power outside here for this. You don't have a power outside for that. If you had a power for these irreducible quadratic factors, that's coming up. That's case 4. So you have here non-factorable quadratic factors in the denominator such that they are not factorable beyond this. They're irreducible, but they're non-repeating. You see that? There's no power on the outside. That's case 3. When we do have a power for these irreducible quadratic factors, that would be case 4, and we're going to talk about it in a few minutes. But these are non-repeating, so that's case 3. So I want to make sure that you have this in your note, because I know some people are not going to watch this video. They're going to go straight to the lecture notes, so they should have this. So we note that in this expression, we have non-factorable, i.e. irreducible quadratic factors in the denominator. Okay. So how do we then write the partial fractions for this? Here's what we do. So we have the left side equals, now remember how what we did in the previous examples, we just had A, B, C, right? We can't do that here. We should have, when we have irreducible quadratic factors that are non-repeating, we should have ax plus b divided by each of those irreducible quadratic factors. So x squared plus 1 plus, we've already used up a and b, so we say cx plus d divided by x squared plus 4. I hope you caught this transition here. We used to have just a over that, b over that, no more, because we have irreducible or non-factorable quadratic factors in the denominator. So we have to have ax plus b over x squared plus 1, cx plus d over x squared plus 4. The idea here is that now in the numerator we have a factor of x. We should include that. All right? All right, so now that we have that, let's see. I should, by the way, before I post these lecture notes on Canvas, I'm going to make a note here for myself. I need to put this in factored form. Sorry, I just missed it. So this has to be, because we already factored the denominator, right? So I should have started the left-hand side with this in factored form. Don't worry about it, because this is just, I'm recording the video. I can't change it now. But when I go to my desk, I will replace this with these two factors. So I will make that change when I finish the video. But I'm just mentioning it now so you know once we factor this, we won't go back to this. We have to start with that factored form. That's why we have on the right side x squared plus 1 and x squared plus 4. Okay? So do you remember what we do at this point? We will clear fractions from on both sides by multiplying both sides by this factor, which I should have written here. Sorry. Imagine that this is that. Okay? All right. So I'm going to write it down. Like I say, some people don't watch the video. They just go straight to my lecture notes. So to clear all fractions on both sides, multiply both sides by x squared plus 1 times x squared plus 4, right? That factor. We know that's going to clear the fractions on this side and clear the fractions on that side. So let me set it up. So like that. X squared plus 1 times x squared plus 4 multiplied by the left side, right? Now I'm not going to make the same mistake here. I'm going to rewrite this with factored form. So x cubed minus 2x squared plus x plus 1 divided by the factored form, this form. Okay? So I'm going to write it like that. All right, that's nice. So equals the same factors multiplied by all of the right side. Remember, we can't do something to one side of the equation and not do the same thing to the other side, right? So let's do that. Multiplied by all of that. So ax plus b divided by x squared plus 1 plus cx plus d divided by x squared plus 4, like that. Okay? So let's distribute on the left and on the right. On the left, things are looking good because this and this cancel each other out. This and this cancel each other out. We get just the numerator, right? We get x cubed minus 2x squared plus x plus 1 equals, now let's distribute this to each of the fractions on the right side. So I have x squared plus 1 times x squared plus 4 times the first fraction, which is ax plus b, divided by x squared plus 1, plus, distribute this into the second fraction, x squared plus 1 times x squared plus 4 multiplied by cx plus d over x squared plus 4, like that. Okay. Now, the left side is okay. There's no fractions on this side. But let's simplify the right side. So I'll start with the same expression on this side. So we have x cubed minus 2x squared plus x plus 1 equals. Notice that this expression and this expression cancel each other out. We get x squared plus 4 times, so we get, let me switch colors here, x squared plus 4 times ax plus b, right? Look how nicely the fraction is now gone. We have no fractions here, plus, now this x squared plus 4 and this x squared plus 4 cancel each other out. We end up with x squared plus 1 times cx plus d. Right? All right. So now what do we have to do? Do you remember what we do next? We're going to distribute things on the right side. So let's do that. So I have x cubed minus 2x squared plus x plus 1 equals, we have x squared times ax, we get ax cubed. X squared times b, we get b x squared. Now 4 times ax, we get 4ax. 4 times b, we get 4b, right? We do the same thing. We FOIL these two. So x squared times cx, we get cx cubed. X squared times d, we get dx squared. 1 times cx, we get cx. 1 times d, we get d. Right? What do we do now? Do you remember what we do now? We group anything that has the similar x term. So x cubes are grouped together, x squareds are grouped together, x terms are grouped together, and constants are grouped together on the right side. So let's do that. So we have on the left, things are good. So now I'm going to use parentheses to group these. Ax cubed plus cx cubed, right? Plus, now the x squared terms, bx squared plus dx squared, right? Now the x terms, plus, looks like I'm going to run out of room. I'll try to fit it in. So plus 4ax, that's 4ax, plus cx, that one, and of course plus the constants, 4b and d. Barely I was able to fit it, right? Barely. I had just a little bit before I ran out of room there. All right, so what do we do now? Do you remember what we do now? We will factor out the x cubed from this group, x squared from this group, x from this group, and we leave the constants as that. So let's do that. On the left, we have x squared, x cubed minus 2x squared plus x plus 1 equals, we have a plus c times x cubed plus b plus d times x squared plus 4a plus c times x plus, of course, 4b plus d. Like that. Okay, do you remember what we do next? Pause the video, do it. We're going to have to write down the system, right? This is where we write down the system. Because this is where, see, so far we've done so much detailed work, right? All of this is quite detailed. But now it's time to zoom out. You're going to have to look at the big picture, not the details. Look at the big picture. If the left side is equal to be equal to the right side, right? The emphasis is on this equality. Then the coefficient of the x cubed on this side must be equal to a plus c. The coefficient of the x squared on this side must be equal to b plus d. The coefficient of the x term must be equal to 4a plus c, and the constant term on this side should be equal to 4b plus d. Right? So let us write the system. Do it before you see my solution. So pause the video and do it on your own, please, and then come back to the video. I'm counting on you to do this, guys. Okay. So I'm assuming you've done that, and now you're back. So I'm going to write down the system. We have a plus c must be equal to 1, right? A plus c must be equal to 1. B plus d must be equal to negative 2. B plus d, sorry. B plus d must be equal to negative 2. 4a plus c must be equal to 1. And finally, 4b plus d must be equal to 1. Right? So if you look at these four equations, it seems that there are this pair that have the same variable in them and this pair that have the same variable b and d in them. So let's pair the equations that have similar variables with each other. So this one has a plus c, and that one has a and c. So let's pair them together. So we get a plus c equals 1, and 4a plus c equals 1, right? How about the other two? The other two are b plus d equals that one and this one. They both have b and d in them, so we're going to pair them up. We have b plus d equals negative 2, and 4b plus d equals 1. Now, these are pretty simple and straightforward systems, right? So I trust you're not going to need me show you how to solve this one for A and C and how to solve this system for B and D, right? I'm sure you all can do that. So let me write the answer to save time. So if you solve this for A and C, we should get A, and we don't need that slide anymore, so we can get it out of the way. So here we know that A is equal to 0 and C equals 1. But I expect you to do this on your own scratch paper and make sure you get the same answers. And if you don't, then come let me know, because maybe I should fix this, and I will. But let me know if your answer doesn't match these. So from this group, we know how to find B and D, right? B should be equal to 1 equals D is equal to minus 3. Okay, so knowing that, we can easily, of course, write down the original, the partial fractions. So knowing that, let me just write down what we started with. We started with this set of partial fractions. So we had x cubed minus 2x squared plus x plus 1 divided by x squared plus 1 times x squared plus 4 equals ax plus b, right, over x squared plus 1 plus cx plus d divided by x squared plus 4, right? And you can still see, let me move this up a little bit, so you can still see a, b, c, d, right? So we're just gonna plug in. We're gonna write down x cubed minus 2x squared plus x plus 1 divided by the factored form of the denominator, which is x squared plus 1 times x squared plus 4 equals, so a is 0, so that means this term will cancel out. B is 1, so we end up with just 1 divided by x squared plus 1, and then plus c is 1, so it'll be x, and then d is minus 3, so minus 3 divided by x squared plus 4. So let me move this up. And I know I've said this before, but I want to remind you again, in Calculus 2 and beyond, it would be impossible to apply some techniques to this rational function, but it'll be quite much easier, I should say, much easier to apply those techniques to either of these two fractions. Okay? So that's why we're learning this technique now. All right, so this was case 3. What is case 4 then? So case 4, and this should be, so this would be page 12 here. Page 12, case 4 is this one, all right? Is when we have a rational function such that qx means the denominator contains repeated, irreducible, non-factorable quadratic factors such that you have repeated ones. See that power? That means the quadratic factors now can be, they don't have to be, repeated. This is case 4. Case 3 was that these irreducible, non-factorable quadratic factors in the denominator were not repeated. So they didn't have a power on the outside. But case 4 is it's possible that we have quadratic factors, irreducible ones, non-factorable quadratic factors that have an outside power, that are repeated. Then the partial fractions will be of this form. Okay? So you start with this, and I should actually, let me see. So you notice that this, with the repeated ones, see, with the repeated ones, r can be any positive integer. So the first one will be no power, right? I mean power 1. Then the next one will be higher power. It's the same thing as that, but the power increases one at a time until we reach the highest power that we have. So if you have this quadratic factor has a power 5, you have to start with 1, then you go to 2, then plus another one, power 3, another one, power 4, and the last one, this will be 5. Okay. All right, so let's see an example of this kind. Like that. So you see right away that this is a linear factor, right? This falls in the category of case 1 or case 2. Case 1, actually. But this one is case 4 because you have an irreducible or non-factorable quadratic expression here as a factor which is repeated. It has a power higher than 1, so it's repeated. Okay, so that's case 4. So let us find the partial fractions of that. So first, so here's the solution. And we start with what we have, x to the 4th plus 1 divided by x times x squared plus 1 squared equals, for this linear factor, for this one, do you remember how we do, what's the format for that, for linear factors? It's just a over x. Now, if you had x squared, it would be b over x squared. If you had x cubed, you would have c over x cubed. You would have to increase the power of the denominator until you would get to the repeated, the highest power of that. This is for repeated factors. But this is linear and it's non-repeating, so it's just a over x. And the next one, we have a quadratic, non-irreducible quadratic factor that is repeating. So we say bx plus c divided by x squared plus 1 to power 1, right? And then the next fraction will be the second power, this one. So we say dx plus e divided by x squared plus 1 squared. If we had a cubed, then we would say fx plus g over x squared plus 1 cubed, and on and on. Okay? So now, do you remember what we do next? We did, after this, we did a similar case for case 3. I recommend you that to pause the video, please. Finish the solution on your own, and then come back to the video to compare your solution with this. I highly recommend that you do that. All right, so I'm assuming you've done that, and now you're back. So we multiply both sides by the factor, which is that will clear all fractions on both sides, right? X times x squared plus 1 squared. To clear all fractions on both sides. Okay. So let us do that. I will multiply that by the left side first. So x times x squared plus 1 squared times all of that left side. X to the 4th plus 1 divided by x times x squared plus 1 squared. You can see that that will clear that fraction easily, right? Equals all of that multiplied by the entire right side. So we have x times x squared plus 1 squared times a over x plus bx plus c divided by x squared plus 1 plus dx plus e over x squared plus 1 squared, like that. Okay? So let's simplify. We've done that several times. We know exactly how it's done. So all of this and all of this cancel out very nicely. On the left, we end up with a very nice and easy expression, which is x to the 4th plus 1 equals. Now on the right, I'm going to distribute this to each fraction first, then simplify. So I have x times x squared plus 1 squared times a over x plus x times x squared plus 1 squared times all of that bx plus c over x squared plus 1 plus that again distributed to this one, right? So x times x squared plus 1 squared multiplied by dx plus e divided by x squared plus 1 squared, like that. Okay? All right. So the left side is okay, but we're going to have to simplify the right side. So let me start with the x to the 4th plus 1 equals. Now x and x cancel each other out. We end up with that x squared plus 1 squared times a, right? The next term, x squared, so this x squared plus 1, one factor of this, because this is repeating, right? It has a power 2. But this and this cancel, so we're left with plus this x which didn't cancel times the other repeating factor that didn't cancel, right? This is squared, this is just has power 1. So x squared plus 1 with power 1, the one that didn't cancel, times bx plus c, right? Plus the last term, so this one cancels out with this one, we end up with x times dx plus e. Look at that. Fractions are all gone. That's what we wanted. What do we do now? Do you remember? What we do is we expand this, FOIL this, expand this, and then distribute next, right? So let's do that. So x to the 4th plus 1 equals, let's expand this, we get x to the 4th plus 2x squared plus 1 times a. Next, we have to, let's see. So what I'm going to do is multiply this x into that, and then in the next step, I will FOIL that. So let's do it that way. So plus x cubed, I'm just distributing this x cubed plus x times bx plus c, and then I'm going to distribute this x into that. I get dx squared plus ex, right? All right, so next step. So let's take this one step further. So x to the 4th plus 1 on the left side. Now I'm going to distribute this a into everything here. What I get is a times x to the 4th plus 2a x squared plus a, right? Now let's FOIL this. So bx cubed times bx gives us bx to the 4th power. X cubed times c gives us c times x cubed. Now let's distribute this x into this parenthesis. So x times bx, we get bx squared. X times c, we get, let's see, and we get cx. I'm just double checking here. Bx plus cx, cx, like that. So let me turn the lights on here, because in the room the lights went out because It does that when you have motionless. So let me go and turn the lights on in this. I'll be right back. As soon as I turn the lights on. Okay. All right, so I turned the lights back on. Sorry about that. All right. So we can continue. And then I'm just going to double check what I did. So plus cx cubed is right here. Bx squared is right here. So everything looks good. So of course the last two terms, right? Plus dx squared plus ex. All right. So now, what do we do now? Remember? Do you remember what we do next? We should group all the terms that have the similar x factor. So x to the fourth, we have to group those. X squared, we group those. This x cubed is just by itself, so we can't group it with anything. But then x terms, we have 1, 2, and we have to group those. So we group similar terms that have similar x terms. So x to the fourth plus 1 equals, these two grouped together, we have ax to the fourth plus bx to the fourth, right? Plus the x squared terms. We have 2ax squared plus bx squared plus dx squared, right? Then the x terms. Well, I should have put the cx cubed here, but that's okay. I'll put it here and then put it in the right order. So the powers are descending. But that, let me by itself, plus cx cubed. And then plus, now the x terms, plus we have c and e, right? So cx plus ex plus, there's the only constant is just this a. That's the only term without any x attached to it. So plus a. Okay, so let's factor. So the right side, so we have this equals a plus b times x to the fourth plus 2a plus b plus d times, I will fix this, guys. This cx cubed should be in the middle here. So x squared, I will fix this after I do this video. I will replace that with the right form. So cx x squared times that, and then plus cx cubed plus, factor out the x, we have c plus e times x plus a, right? Okay, so now something is because we had just one constant here, something really interesting happens because we have just one constant term. We don't have minus 2a plus b equals something, right? Because if you now replace or substitute for x with 0 in all of these drop out except a on both sides. So on both sides, if you substitute for x with 0, what happens? You get 1 equals a. That's great because we can right away solve for a without setting up any system. So that's good. Let's take advantage of that. And again, this happens because we have just one constant term. So put 0 for x on both sides. They cancel out. You end up with a equals 1. So if x equals 0 on both sides, Then we have A equals 1. A equals 1. Very nice, right? So now we can set up the system. Let me bring my next page. I will keep that on the screen. Like that. Like that. Okay. So compare, again, we have to zoom out. Look at the big picture now. If both sides of this equation are to be equal, then we have no choice, but A plus B on this side should be equal to 1, which is the coefficient of the x to the fourth term on the left side. So we're going to write down the system. We will say that A plus B must be equal to 1, right? Now, and we already know that A equals 1, right? So let me list it here as well. A equals 1. We know that from here. So because of that, if A equals 1 and A plus B equals 1, then what does that make B to be? B has to be 0, right? B can't be anything else than 0. So 1 plus 0 is 1. So B has to be 0. So we already have that. Great. So next, we have, notice that on the right side, we have cx cubed, right? Cx cubed. But do we have on the left any x cubed term? We don't. So this coefficient must be 0. So C must be equal to 0. Wonderful. We have that one figured out as well. So C equals 0. Then, do we have any, we have x squared on this term, on this side, 2a plus b plus d. Do we have any x squared term on the left side? No. So we know that these, whatever a, b, d, they should all add up to 0. So let's write that down. We have 2a plus b plus d equals 0. So we all look at this. We already have A figured out. We have B figured out. We know C. We can easily figure out D, right? We don't even need C for this equation. So 2 times 1, which we know A is equal to, plus B, which is 0, plus D must be equal to 0, right? That's this equation. So 2 plus 0 plus D equals 0. Therefore, D must be equal to negative 2. You see that? Great. So we have A, we have B, we have C, we have D. So the last thing, here, we have C plus E that are factors of x. On the left side, do we have an x? There's no x on the left. So C plus E must add up to 0. So let's write it down. C plus E must be equal to 0. So like that. So C, we already know what C is. C equals 0 plus E equals 0, right? So if 0 plus E is equal to 0, E has no choice but to be equal to 0. So we have E as well. So the fact that we recognize that we can take advantage of the fact that on the right side, there's only one constant and it should be equal to 1, that worked out quickly to our advantage to obtain the other values, right? All right. So now we have all the variables figured out, so we can go ahead and write down our partial fractions. So let's remind ourselves what we started with. So we started with this setup, with this format. We had x to the fourth plus 1 divided by x times x squared plus 1 squared equals a over x plus bx plus c over x squared plus 1 plus dx plus e divided by x squared plus 1 squared, right? That's what we started with. Now, so let me write those here. Given, because it's off the screen now, so given that a equals 1, b equals 0, c equals 0, d equals negative 2, and e is equal to 0, we can certainly write down the partial fractions, right? So we end up with x to the fourth plus 1 divided by x times x squared plus 1 squared equals a is 1, so 1 over x. How neat is that, right? So in Calculus 2, there is a method that we can apply this to this very easily, but not to that so much. This is going to be a very complicated expression, but this is very easy expression to handle with techniques in Calculus 2. Then plus b is equal to 0. So that term drops out. And guess what? C is also equal to 0. So we end up with 0 divided by x squared plus 1. 0 over anything is 0. So this will be 0. I'll cancel it in the next step. Now plus d is minus 2. So minus 2x plus e is 0, right? So I just leave it out and I divide that by x squared plus 1 squared. Okay, let's tidy this up in the final solution. We have x to the fourth plus 1 divided by x times x squared plus 1 squared equals 1 over x. 0 divided by anything is 0, so this is just 0, right? This is just 0. Now this minus multiplies this by this, it makes it negative. So minus 2x divided by that, x squared plus 1 squared. And this is our final partial fractions on the right side. So we went through all possible 4 cases, and I hope this was useful to you, and I thank you for watching this video, and I hope if you have any questions, you'll come and see me during the office hours. So for now, have a good day, and I'll see you in class.